we'll get started. So thanks everyone for coming to lecture. I'm clearly not your professor. She is currently, I think, in some, she's doing something else, and she asked me to fill in for today. The lecture topic for today is something called SOCP, or Second Order Conic Program. And so in the past two lectures, you all have covered linear programs and quadratic programs, right? SOCP is another class of convex optimization problems, which are more general than both linear programs and convex quadratic programs, but are still tractable and possible to solve. Okay? And the form of an SOCP looks kind of strange, and so in order to motivate the concept a little bit, we're going to start with some example. Okay? So suppose that you're Amazon, right? Suppose that you're employed at Amazon and you're in charge of figuring out their logistics. Okay? The goal here is that you have a bunch of different truck stops. Okay? You have truck stops. Say X1, X2, X3, and then, I don't know, X4. Okay? By the way, everyone in the back can see okay? Cool, great. And you want to place your warehouse. You want to place a warehouse that can serve these truck stops. Okay? And one natural way to do this is to solve an optimization problem with a particular objective, which will guide you to place the best location for your warehouse. Okay? So one thing that we want is that we want this warehouse to be sort of central to all these points. Okay? So it should be somewhere in the middle. Okay? Okay, somewhere like there. But the precise way that we find this warehouse position X is by solving, again, an optimization problem. So one way to do this is something that you all already know how to do. Okay? This I'm going to call problem 1. It's a minimization problem over X in the plane, for example, if you're plotting things on a 2D grid, of the average sum of squared distances. Okay? This thing is, well, this objective is a quadratic function, a convex quadratic in X. So you know how to solve this. You can take the derivative and set it to 0. The point is that you should find the X which is somehow best to serve all the warehouses, the warehouse which is best placed to serve all the bus stops. And the precise way which we mean by best served is guided by the objective function. Yeah, that's a good question. Yeah, does it make sense now? Yeah, good. Yeah. So this is like one particular formulation, and this is one you already know how to solve. Okay. The second formulation is maybe a little bit more like first principles than this one. Okay. So can anyone tell me why we actually prefer square distances here, other than you already know how to solve this problem? Okay. Yeah, go for it if you want. Yeah, good. Yeah, so basically the reasons that we choose the square distance is that it's easy to handle, right? Easy to work with. Okay, that's great. But suppose that this is like some major operation and you really want to get this right, even at the cost of messing up. Even at the cost of being less computationally tractable. Okay. Then this leads to problem 2. Min over X in R2 of the average distance, average not squared distance. Okay? This is not a quadratic objective. Okay? These problems are equivalent if and only if there is exactly one truck stop that you're serving. Okay, and then you place the warehouse right next to the truck stop. But if there's more than one, right, this second one is not a quadratic function. It's a sum of square roots of some things, okay? Because the 2 norm is a square root of something. Okay, this is not quadratic. Yet, so because it's not quadratic, this problem is not a QP. Okay, it's not a quadratic program, therefore not a linear program. Okay, but we're going to show later on in this lecture how exactly to solve this problem by casting it to a second order Con program. Okay, So this is one motivating example. The second one is, suppose you even have a different constraint than minimizing the sum of distances. Suppose that you want it to not be too far from any one particular, suppose you want the warehouse to be not too far from any particular truck stop, okay? Maybe this is more reasonable because each truck only has a finite amount of gas, and so you want to make sure that none of the trucks burn too much gas on the way to the warehouse and back, okay? So this could be min over x in R2, max over I, going from 1 through n, of x minus xi 2 norm. Okay? So not only is this function not quadratic or linear, it's not even differentiable. Okay? Because this max is makes non-differentiability at the part where there's two equidistant warehouses, for example. Cool. Okay. I'll pick those up later. But okay, so this problem 3 is also castable as a second-order cone program.
Sorry, so this is really question. Is this problem equivalent to the same problem, but then we take the square of the two norms?
So you're saying that is problem 2 equivalent to problem 1, or problem 3 equivalent to problem 1?
No, I was just saying could we rewrite problem 3 as the same problem except just square the two norms?
Yeah, so you get the same solutions. Yeah, I agree. Yeah, you totally get the same solutions. Yeah, good. So the question was, if it wasn't audible, the question was, can we write problem 3 by putting a 2 norm here? And the answer is yes. That's totally fine. Because for each one of these individual terms, the max, if it's max over I of this norm, then it's max over I of this norm squared. Okay, because the square is a monotonic function. But for this one, it's like the sum of square roots. And although squaring the sum of square roots is not a monotonic function of the input. Okay, good. Yeah, that was a very good question. Okay, cool. Yeah, so problem 1 is something you know how to solve. Problem 2 and 3 are maybe more natural objectives, which are castable as SOCP. And so in the next however many minutes, we're going to figure out how to do that. Okay? So in order to understand SOCP, actually maybe I'll use this board, we need to understand what a cone is. Okay? So SOCP stands for second order cone program. First we need to understand what a cone is. Okay? So let me give you a definition. A cone is a subset A of Rn such that for every vector v in this cone and every alpha in, just say alpha greater than 0, we have that alpha v is contained in this cone. Okay, so what does this actually look like? Right, so this is just some math definition, and it's always easier to figure out what it looks like graphically. So let's give some examples of what a cone looks like. I'm going to give you just the top right quadrant of R2, and let me draw you a cone. Okay, this one goes off to infinity. Okay, this is our cone K. Okay, why is this a cone? We take any vector here, then the set of all alpha greater than 0, so the set of all alpha times v for all alpha greater than 0 manifests as a ray starting from the origin and going through this point to infinity. And because of the shape of this cone, this ray is contained in this cone for all alpha. Yeah. As you go off to infinity. Okay. Yes, so you can equivalently state the definition of a cone as saying that it contains all rays through any of its points starting from 0. Okay. Questions? Okay, so this is an example of a so-called convex cone, which is a cone which is a convex set. But there are cones which are not convex. For example, let me give you all of R2 this time. Let's start with the same cone. and let's give you its mirror image. Okay, and let's say this is all one set K. Okay, both the top half and the bottom half are all the same set. Okay, why? Okay, this is a cone because if you take any ray, you can see that any ray going through 0 through any of the points in the cone, it'll stay in the cone. However, it's not convex. Why? If we take a point here, take this point, draw the line between them, goes outside the cone. Okay. So there are cones that are not convex, and so yeah, I just wanted to give that example. Okay, so the thing is that cones are like very so the thing is that cones are very useful for more in-depth like convex analysis, and optimization. But for this class, the only cone that we'll like actually talk about is the so-called second-order cone. Let me write it on the central board. The definition. Okay, the second-order cone. So SOC is second-order cone in Rn plus 1 is the set. Okay, this is the set Kn, which is defined to be the set of all x comma t, such that x is Rn in Rn, t is in R, and the 2 norm of x is less than or equal to 2. Okay. And if you remember your definitions of like convex sets from earlier this semester, this is the epigraph of the L2 norm in Rn. Okay. So this is a subset of Rn plus 1, even though it's defined as Kn, because the input x is in Rn. Okay, so what does this actually look like? So as the epigraph of the 2 norm, it's possible to draw K1, right? Because K1 is a subset of R2, so it's possible to draw that one. Okay, and if you're a better artist than me, maybe it's also possible to draw K2, which is a subset of R3. But I feel like I would mess it up really badly, so let's not do that. Okay, so this is R2. And since the epigraph of the 2 norm in one dimension is the absolute value. So imagining this is the graph of the absolute value function, this is K1. That kind of, the professor would call it ice cream cone. Right? It just starts at the origin and points up in both ways, like a particularly wide ice cream cone. Go for it, yeah.
Is there some relation to the norm ball? Like the formation seems similar, but like different. I don't know.
Kind of. This is like saying like okay, so if you fix t, then the remaining like values of x will be the t normal.
So the cross sections.
Yeah, the cross sections, exactly, yes. Good, very good question. Go for it, yeah.
What does SLC stand for?
Second order cone. Go for it.
How is that a cone? It looks like a hyperbola.
So these are supposed to be straight lines. I apologize for screwing up the drawing.
That one.
Oh, the which one?
The non-convex cone usually.
Okay, good. Let me. Okay, so the definition of a cone is that it's a set that contains all its rays through 0, right? So we take any point here, and we draw its ray through 0. We'll see it's contained in the cone K. If we draw any point here, we draw its ray through 0. We'll see it's contained in the cone K. Okay, that's the definition. Yeah. Go for it. Oh, yes. So this should be x I mean, I draw it as vector, but it's like really a scalar. And then this one should be t. No, here x is in R1. Yeah. Which is why it's K1. Okay? So the dimension of x is like, or the dimension of K is the number of entries in x. Yeah. Good questions. Okay. So, oh yeah, sorry, go for it. Oh, I don't think so. I don't know the answer off the top of my head, but I feel like I feel like that's not true because I think there's also a first order cone, which is not the one norm. Yeah. Yeah, good question. Yeah. Maybe you can look that up. Yeah, go for it. Yeah.
So the x in the function is just a scalar, right?
Yes. 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 Yeah. Okay. Cool. So the first things I want to talk about the second order cone is that it's a convex cone. Okay, so you can see why it's a convex cone from this drawing, but it's true in any dimension. Sorry, was there one more hand? I think I may have seen one more hand. Okay, no, I guess. Okay. Yeah. So proposition can is a convex cone. Okay, so convex. Okay, so why is Kn convex cone? It's because it's the epigraph of the 2 norm. Okay? I'm going to write epi of the 2 norm. Okay, so the 2 norm is a convex function, so its epigraph is a convex set. Okay, and therefore Kn is convex. Why is it a cone? So let x comma t in Kn. So this as a reminder, x is a length n vector and t is a scalar. So this thing is really a vector in Rn plus 1. And so x comma t is in Kn, and let alpha greater than 0. And we want to show alpha times x comma t is in Kn. Okay? This claim makes sense. Like, does it make sense why it would prove that Kn is a cone? Okay. Please feel free to ask at any time. Yeah. Okay. So how do we show that alpha times the vector x comma t is in Kn? We're just going to look at the definition of the second order cone. So first of all, alpha x comma t is the vector alpha times x comma alpha times t. Okay, this is still a vector in Rn plus 1. Okay? And to check that this vector is in Kn, we just need to take the 2 norm of the first component and show that it's less than or equal to the second component. Okay? Alpha times x, 2 norm of that, because the 2 norm, because you could take scalars outside of the 2 norm, and because alpha is greater than or equal to 0, this is equal to alpha times the 2 norm of x. And because x comma t is in the second order cone, we know that norm of x is less than or equal to t. So this is just less than or equal to alpha t. Okay? So we now know that norm of alpha x is less than or equal to alpha t. And this proves that alpha x comma t is in the second order cone. Okay. And this completes the proof. We define Kn. So we call it the second order cone because it is indeed a cone. But if you look here, the definition of Kn is like not referring to the definition of cone at all. Okay? And so we actually need to back up our claim that it's a cone. Yeah. Yeah. In the back. Want to show. Go for it. because we say that let x comma t is in Kn, right? And Kn is just the set of all x comma t such that norm x is less than or equal to t. Okay, so by assumption, we've said that norm x less than or equal to t. And so then we can use that assumption over here. Cool. Make sense? Well, okay, so we want to show that for any alpha greater than 0 and any x comma t inside the set, we want to show that alpha times the x comma t is also inside the set, okay? Because this is definition of a cone. This is over here, it's definition of a cone. For any vector in the cone, any alpha greater than 0, alpha times v is in the cone. Okay? And if you just do this two inequalities over here, you'll show that alpha times xt is also in the cone, is in the set, and that makes the set a cone. Here to here?
Yeah.
Okay, so this is because of the definition of Kn. Right? Kn is all the points x comma t, or in this case, alpha x comma alpha t, such that the 2 norm of alpha x is less than or equal to the alpha t. Okay, this is just the definition. Yeah. Yeah, so let's first, okay, so we're going to start now to define an SOCP. And let us first actually discuss what a second order cone constraint is. The second order cone constraint, so maybe definition, a SOC constraint is a constraint of the form okay? So given an optimization variable x, your constraint is of the form. Let me write this a little bigger. Ax plus b, comma, c transpose x plus d is inside the second order cone of some dimension, okay? Because A can be whatever matrix. Okay, so given an optimization variable x, this is what a second order cone constraint looks like. So more generally, this first constraint is an affine function of x, and the first entry is affine function of x. The second entry is also affine function of x. So what this is saying is that the second order cone constraint is just the affine function of x, comma affine function of x is inside this second order cone. Yeah, sorry, go for it. Any question? Yeah, and so this is equivalent to saying that, which you'll see in a much more common form, it's equivalent to saying absolute value, norm of ax plus b less than or equal to c transpose x plus d. Okay, so norm of an affine function of x less than or equal to another affine function of x. Okay. Answer your question? Okay, so sorry, yeah, so I didn't do the best job precisely defining everything. So c here is a column vector of length n. So if x is a vector of length n, then c is also a vector of length n. That's how you could take the c transpose x. So if you just didn't write the transpose, then you would have an invalid matrix multiplication, right? So you'd have two column vectors of length n, like right next to each other. It's not valid. Like it's like the syntax doesn't, like if you wrote it in Python program, the Python program would not compile. So it's like not valid. Yeah, good question. Go for it. Yes, exactly. I mean, yeah. So this one is like the x vector in the definition of the second order cone, and this one is the t vector in the definition of the second order cone. There's a t scalar. Yeah. It's the second order cone of dimension m. It's the second order cone of dimension m, which is a subset of R m plus 1. Go for it. Oh, yes, good. Oh, shoot. Good. Okay. Good questions all, and thank you for the correction. Okay. So now let's define an SOCP. Okay. definition. An SOCP is a optimization problem underline the wrong word, of the form min over x, say an Rn, C transpose x, subject to AX, oh, so AIX plus BI less than or equal to CIX plus DI. Okay, and then this is for all I in some 1 through m. Okay, I realize here that the m over here is not the same thing as the km over there. This is not the same m as the km over there. Sorry about that. Yeah, but this is the definition of a second-order cone program. So if you can write, so it's a linear objective and a bunch of second-order cone constraints. Okay. Go for it, yeah. Yes, exactly. So it's like the same thing as f in the objective has nothing to do with fi in the constraints. Let me get a better chalk. Okay. Good. Yes.
Okay.
MCIs, yeah. MDIs, MAIs, and MBIs. Okay, cool. So here's the, okay, so here's one of the big reasons why we care about SOCP. Sorry, go for it. Yeah.
Wait, did you say that the CI and the C in the objective function are two different things?
Yes. Yeah. Maybe we could say this one is C0. I don't know. Doesn't matter. Yeah, so this one is C0, and then the rest are CIs from 1 through m. Okay. All right, so here's the reason that we care about SOCPs is like, one of the reasons is that we can model a lot of problems using SOCPs. And the demonstration of that I promised you at the beginning, and we'll get to shortly. The second reason is that they're easy to solve. Okay, the way to solve them, there's several ways to solve them. One of the ways to solve them is interior point method, which you'll probably, hopefully learn by the end of this course. And then you could also use like specialized methods like conic programming, which are a bit beyond the scope of this course, but maybe you'll see in other algorithm courses. Okay. And all of this kind of rests on the fact that SOCPs, if you could write a problem of this form, then it's a convex problem. So proposition, I won't prove this, but you can try to prove it yourself. SOCPs are convex. Okay? Go for it, yeah, in the back.
If we have other types of constraints like affine or quadratic on top of that, is it still SOC?
Good, yes. So I'll prove shortly, maybe after an example or two, that linear programs and quadratic programs are both instances of SOCPs, or convex quadratic programs, I mean, sorry, yeah. You could also prove, and it's in the course reader, that quadratically constrained quadratic programs, meaning the quadratic programs with also, and you also add on like convex quadratic constraints, those are also SOCPs, okay? But for brevity, I won't do it in the lecture. You can look up the proof in the reader. Yeah. Okay. Cool. Very nice. Okay. So yeah. So let's actually continue this example, and I want to do it on this board over here. So is everyone okay with me erasing definition of a cone? Okay. Speak now or forever hold your peace. Okay. So now that we know the definition of SOCP, and we've sort of convinced ourselves that it's tractable to solve one of these problems. Now we want to go about showing how these problems that we started with for motivation are examples of SOCPs. Okay? So problem 1 is a quadratic program. No need to go especially there. We'll talk about later about how QPs are SOCPs. Problems 2 and 3 are not quadratic programs, and so we'll need to explain how and why they're especially SOCPs now. Yeah, go for it.
Wait, sorry, Barry. So for all these problems, we don't have any constraints, right?
Yes, there's no constraints. Okay. I mean, you could add like affine constraints or whatever, and it still would not change that eventual conclusion. Oh. But like in this original formulation, it's okay to not have any constraints. Yeah. Go for it.
How did we convince ourselves that they're tractable?
Because it's convex.
Okay.
Convex problems are tractable. Gradient descent, interior point method, specialized convex programming. Yeah.
What is tractable?
Solvable, like solvable efficiently. Yeah. So it's just called second order cone. I think there's also a first order cone, but I don't recall the definition of that right now. Yeah. Yeah. No, you're good. Yeah. Y'all, no, these are not silly questions. Okay, these are really good questions. So don't apologize. It's fine. Okay, good. So let's start with problem 2. Okay, want to show that problem 2 is an SOCP. Or at least you can write it as an SOCP, and you can solve a SOCP, which will give you the same answer as this one. Okay, how do we do that? So we have objective here. Min over x. Could be in whatever dimension now. It doesn't really matter. 1 by n, sum from I equals 1 to n, x minus xi, just 2 norm. Okay, so the defining aspect of SOCPs, as you may have intuited, is that as per the definition of a second order constraint, cone constraint, the defining aspect of second order cone constraint is that you get to put in norms now. Okay, you get to involve norms in your constraints. Okay, but if you look at the definition of second order cone program, the objective is linear. Okay, so given some complex function in the objective that you want to transfer over to the constraints, how have you done that previously? Go for it. Good, slack variable, exactly. So here, we're also going to use slack variable. Okay, so just going to call this the solution. Slack variables. So let ti be a slack variable which is always greater than or equal to x minus xi. Okay, this is like a reasonable slack variable to put in. Then we can write this optimization problem as min over x and t of 1 by n, sum from I equals 1 to n of ti subject to x minus xi, 2 norm less than or equal to ti for all I. Okay? Why is this an acceptable substitution? So first of all, these have the same solution because the objective will prioritize minimizing the t's, and so they'll always take the minimum value subject to the fact that they're greater than or equal to this norm. Okay, so at optimum, they're always going to be equal to this norm. Okay, and then from there, if you make that substitution, it's the same objective. So these are the same problems. Go for it. Yeah.
Sorry, could you explain that again?
Yes. So at optimum, right? So this objective will support minimizing the t's as much as possible, subject to the fact that they're each greater than this norm over here. Right? For each I, ti is greater than or equal to this norm. And so at optimum, they're all going to be equal to this norm. Right? For the optimum x. For the optimum x comma t, I mean. Yeah. Okay? And then once you make that substitution that the optimal t is equal to the optimal x minus xi norm, right? Then it becomes the same objective. Yeah. Okay. So that's one claim, that these two problems have the same solution. Let's call this 2 prime or 2 star, let's say. And the other thing I want to prove is that problem 2 star is the SOCP. Okay? the objective, so now the optimization variables are both x and t. Okay? The objective is a linear function even of x and t. And the constraints, well, this one is an affine function of x and t. Of x comma t. And then this one is also an affine function of x comma t. Oh, this t should also be vector. Yeah. Okay? So,
Sorry, TI is it?
yes, it's an affine function. So if you consider the like, just for example, if you consider the vector x comma t in R2, then t is equal to 0, 1 times, yeah, x comma t. Okay, and this is like certainly an affine function of x comma t. Okay, so you could do the same thing. I mean, you could do the same thing, except it'd be a little more complicated in this case, but it's certainly an affine function. Questions? Okay, so this thing is SOCP because this is second order cone constraint, and the objective is linear in the optimization variables. Okay. So this one, problem 2, we're able to solve properly by just solving problem 2 star and then extracting the optimal x star. Okay, let's do the same thing with problem 3. Do you mind if I erase this, by the way? No? Okay. Okay. Problem 3. We're going to say min over x, doesn't really matter the dimension, of max over I of x minus xi to norm. Okay? So this is our problem 3 from earlier. Sorry, there's a question there?
Sorry, just to reiterate, for
Yeah.
2 star, when we introduce a slack variable, is
Yeah.
it to show that 2 can be written as an SOCP?
Yes, exactly, yes. Okay, go for it, yeah.
Sorry. Would we say that the constraints are, or for like the rewritten version, we can say that the constraints are affine in TI?
They're affine in TI, but what you really care about is that they're affine in x comma t, which is like this length n plus n vector. Or m plus n vector, I don't know. I'm omitting the dimensionality here. Yeah,
Okay.
yeah, go for it. Linear, oh yeah, so the thing is, the two conditions are, 1, the objective is a linear function of the optimization variables. Okay? And the second is that all the constraints are second order cone constraints. Okay? That's the two defining things of the two defining properties of SOCP. Go for it. Yeah.
So when you say a linear function, it looks to me like it's not, like it's specifically like an inner product, or can it be any like linear transformation? Like, can we have the objective be some arbitrary like matrix AX?
But then it wouldn't be a scalar, right? So the point of objective function is that it's a scalar which represents the thing you want to optimize. So in order to have a scalar, it needs to be a linear function which takes in a vector and outputs a scalar. And these are all representable by inner products or dot products. So it's fine. Yeah, go for it.
I'm so sorry.
No worries. No.
Aren't the constraints, like, okay, if you look at the n plus 1 like vector that's xt,
This is not n plus 1. This is like, maybe I should use a different variable for Slack, but this is like, if x is dimension m, or x is dimension even 2, then t is dimension n.
yeah, sorry.
This is like n plus 2, let's say.
Okay.
Yeah.
But if you look at that combined,
Yeah.
like, isn't this is not affine in that combined vector, right? Because it's still the L1 norm of its component. Yeah, L2, sorry.
Sorry, this first one, right? Or
The
you're
second one.
talking about this norm. So it's the norm of an affine function.
Right. But so the constraint itself isn't affine in that.
Exactly, yes. The constraint is not affine, but the thing on the left-hand side is a norm of an affine function.
Okay.
Yeah.
Okay.
Okay, and this is like broader than, I'll show you, it's a little bit broader than just having affine function. Okay? Otherwise, we just have an LP again, right? Because all the constraints would be affine, and the objective is also a linear function. So it'd be a linear program. But this is definitely broader than linear program. Go for it, yeah.
Just to clarify,
Mhm.
for equation 3, you're finding the max value, the difference between the 2 norm, and the difference of the 2 norm, and then minimizing over that, right?
Yeah, we're finding the max value of this distance, this max value of this distance over all the I. And we're finding the point which minimizes the maximum distance. Yeah. Okay. Good. Okay. So the way to do this again is via slack variables again. Okay? This time, it's a single variable. Let this variable t, the single variable t, greater than or equal to max over I of x minus xi. Okay? And because t is greater than or equal to the max, it's greater than or equal to each individual one. Okay? T greater than or equal to x minus xi for all I. Okay? And so our problem 3 star, for example, is going to be min over x and t of just t, subject to t, norm of x minus xi less than or equal to t for all I. Okay, so this is a second order cone program because the objective is an affine function of x and t. And each constraint, you have a 2 norm of an affine function of x and t on the left-hand side, and then the right-hand side is also an affine function of x and t. So we're good. Yeah, so this is a second order cone program. This one? Or, okay. Yeah, so we just introduced another slack variable, right? This is a complicated, okay, so the heuristic here is that this is a complicated objective. Want to see what we can do with it, so we just add a slack variable, okay? That slack variable is just going to be greater than or equal to everything in the inside. And since we're minimizing over it, at optimum, it's going to be equal to everything on the inside, okay? So because it's equal to so because of that, we could say that t, our slack variable, is greater than or equal to all these 2 norms. Okay? And then because of that, it just manifests as the constraints down here. Yeah. Go for it, yeah. Oh, so the left-hand side is the 2 norm of an affine function of x and t. Okay? So the thing inside here is affine function. X minus xi is an affine function of x and t. Go for it.
You did the version there with the square of the dot, and
Yeah.
you did the same process. Could you just get a quadratic program with quadratic constraints?
Yes. But yes, yeah, you definitely would. But you don't need to do this because this is already a quadratic objective function, and you can just solve it directly. It's a convex quadratic. You take its gradient, you set it to 0, you solve for the optimal x. Over problem 3. Oh, I see. Yes. Yeah, you'd get a quadratic constraints. Yeah. Yeah. Go for it.
Could you explain that there are 2 arguments in 3 star, but only 1 argument is in SOC?
Good. Yes. So the 2 problems are, so whenever you introduce slack variables, right, you're always going to end up with more variables than when you started with. However, it's the hope, right, if you set up the slack variables correctly, then you should keep some, like the x over here, when you solve for this x and t, optimal x and t, then if you set up the slack variables correctly, then the optimal x over here is going to be the same optimal x as the one that solves this problem over here, the original problem. Okay, does that make sense? Cool, very good. Good questions, all. Go for it. Yeah.
So the reason why you're emphasizing the fact that our constraints always like an L2, like a 2 norm of an affine function of xt, because
Yes, exactly. This all goes into the claim, or this all goes into the proof of the claim that we can make problems 2 and 3 into SOCPs. Yeah. Go for it.
Very sorry. So I guess like follow up to that one. How do we know that like something that form true norm of affine function is less than equal to t is SOCP? Because that's slightly different from what we have up there, right?
Ah, good. Yeah. Yeah. Okay. So the counterclaim was that it's the definition over here. If you just pattern match the AI, BI, CI, DI, then you should be able to conclude. Yeah. Sorry, in the back. Yeah.
What kind of problem is
Problem 3 is also SOCP.
before we transform it to SOCP?
Oh, I mean, before we transform it, both problem 2 and problem 3 don't like neatly fit into a classification. But like once we do, then they're both SOCPs. Yeah.
So an SOCP problem has SOC constraints?
Yes. Okay. Cool. Let's move on. Okay, so now that we finished our initial example, we're just going to do a little bit more theory before we go back into other examples, if time allows. Let's say. Everyone cool with me erasing this? Yeah. Okay. All right. So, claim. Let's say claim 1. And LP is an SOCP. Okay, so I forget who, but I promised someone at the beginning of the lecture that we'll show how affine constraints are also second-order cone constraints. And this is what we'll do here. Okay. Let's start with this linear program, min over x of C transpose x, C0 transpose x, subject to AI transpose x less than or equal to BI for all I. And we want to show that this is a SOCP. Okay? Yeah, good. So, the way to do this, right? So this is a generic set of affine constraints, and the way to do this is just note that this is equal. Just note that this constraint is equivalent to 0 less than or equal to BI minus AI transpose x. Okay. So the right-hand side is an affine function of x. I will claim that the left-hand side is the norm of an affine function of x. Okay? In particular, it's the norm of the function 0 transpose x. Okay, and then you can also add plus 0 if you want. But in particular, this is the norm of an affine function of x. Okay? And so I mean, this 0 can also even be a 0 matrix. You can add a 0 intercept, whatever you feel like. But 0 is the norm of an affine function of x. And so these constraints are immediately second-order constraints, second-order cone constraints. Okay. So that's LPs. Again, the objective is a linear function of x. So this problem now has linear objective and second-order cone constraint, so it's an SOCP. Now let's do QPs. Maybe let's erase that board, or let's do this board actually. So QPs will be a little bit more involved. And even though I tried to, when preparing this lecture, and also last year when I was writing the course reader, I tried to keep the number of tricks to a minimum. It still involves like one kind of sort of trick. Not expected to reproduce something like that on the exam, of course, or homework. Yeah, and if you go look at the book, it has like 10 tricks in a row. So one is less than 10, I think. Yeah. Okay, so QPs. So min over x, 1/2 x transpose qx plus c transpose x. Okay, c0 transpose x. Why not? Okay, subject to ai transpose x. Sorry?
C not in X.
Oh, yes, thank you. Yeah. AI transpose X less than equal to BI. For all I. Okay, so the affine constraints, you already know, are second order cone constraints, right? We already did that. And this part of the objective is a linear function or affine function of X. And so the only real thing we have to contend with is the quadratic term in the objective. Okay, and we're going to do that now. Again, when we have an optimization problem and we want to transfer some difficulty from the objective to the constraints, we use slack variables. Okay? So this is equivalent to, I'm just going to say that this, I'm just going to say that this AI transpose X less than equal to BI for all I, those are kind of understood. In fact, we can actually solve this problem with no constraints at all, and it's the same idea. So forget about these constraints. And just remember that you can add them in at the end because they are second order cone constraints. And let's just try to solve this problem, okay? And by solve it, I mean phrase it as an SOCP. Okay? So just add another slack variable. Min over x, comma t of t plus c naught transpose x, subject to 1/2 x transpose x, or sorry, x transpose qx less than equal to t. Okay. So at minimum, so at minimum, the t star is going to be equal to x star transpose q times x star. Okay, because that's you're going to find the optimal x, then you're going to make t as small as possible. Okay. Good. So the problem is now, how do we formulate this as a second order cone constraint? Okay. So this will take a little bit of work. Multiply by 2 on both sides. We get x transpose qx less than equal to 2t. Let's just draw this arrow, and then this is if and only if x transpose qx less than equals minus 2t less than equals 0. Okay, so this is just algebra. In just a sec. Yeah. So the idea behind this is now that we want to write everything in this constraint as either a sum or difference of squares. Okay, this is the sort of trick I mentioned. And the reason for this trick, at least the best way I can motivate it, is that we want to be able to take square roots at the end and turn everything into 2 norms. Okay? 2 norms are just linear functions. Okay? And so to this end, we'll use some kind of difference of squares identity. So first of all, x transpose qx. So this is not a trick. X transpose qx is equal to. So because we said q is PSD, q has a PSD square root, q 1/2. That's equal to this thing norm squared. Okay. And just to be complete, let's write this out as q 1/2 x 2 norm squared minus 2t less than equals 0. Okay, so we want to write this as like a difference of squares or like sum of squares. just so we can write things as two norms. And for this, we'll use identity, which is derivable via like just expanding out, like FOIL, basically, which is that let me write this over here. So by FOIL, we get u plus v squared minus u minus v squared is equal to 4 times u times v. Okay? And for the second term, what we shall do is we can write if u is equal to, what did I put here? 1/2. And then v is equal to minus t. Then we obtain that this is equal to q 1/2 x 2 norm squared minus, or sorry, plus 1/2 minus t squared minus 1/2 plus t squared less than equals 0. Okay, so up till here, okay, so from here to here, we kind of use this trick, which is just bestowed upon us by a difference of squares identity. And again, the point of this is that you write everything in terms of sums of squares so that you can take square roots at the end, get two norms back, and it ends up working out. Okay. Cool? Okay. Yeah, go for it.
Wait, sir, why is the two norm, I think you said it was a linear function.
The two norm is not a linear function.
Okay.
Sorry, yeah, sorry, I'm not sure what you're, where you got that from, but if, yeah. Yeah, sorry, I couldn't help you with that. Sorry, what's up?
Can you explain again what the point of doing the FOIL thing was?
So again, the point of doing this FOIL thing is because we want to write everything here as like a sum of squares or a difference of squares. So that at the end, after we rearrange, we can take square roots and we can get two norms, okay? Because the two norm is just a square root of a sum of squares. Okay? That's at least, when I came up with this, that's at least the intuition I had, yeah. Yes, good, yeah. Yes, yeah, good. So SOCPs are convex. And so this should tell you that the only QPs which you can hope to make into SOCP are those which are already convex. Right? If you had a non-convex QP, there's like very little hope to make it into a convex SOCP. Right? Yeah, and so at the beginning, sorry for not making this clear, that's totally my bad. You're completely correct that Q in particular is assumed to be PSD. Okay, go for it, yeah. Sorry, can you repeat that?
Why can't we just convert into the square of
Yeah, so we use this FOIL identity, right? This FOIL identity will just tell us like that we can do this calculation. And indeed, if you expand out this difference of squares, you'll get exactly 2t back.
why can't we just take the square root of 2 if we just want to get the square?
Oh, why can't we? Oh, that's a good question. Yeah, that's a really good question. So the question is, why do we have to go through this whole song and dance? Why can't we just like take square roots and just get like the two norm of like q square root, or sorry, square root of q times x less than equal to square root of 2t? Right? That's a totally valid question. Like that's an amazing question actually. And the answer to that is that square root of 2t, right? So it's, because t is because it's a optimization variable, right? Square root of 2t is not a linear function or affine function of the optimization variables. Okay? So because it's not an affine function of optimization variable, what we'll get at the end is no longer SOCP. Yeah, keep going.
So what if we change the standard variable to square? Then after
if we change the slack variable to t squared? Yes. I see. I see. And the reason that this doesn't work is the following. Okay, that's also a very good question. The reason that doesn't work is the following. So if we wrote like t squared over here and then t squared over here, right? Is that what you want to do? Well, then there's nothing which promotes t to go. Actually, wait. So first of all, if we do this, it's a quadratic objective, right? And so we cannot say that's SOCP because it's a quadratic objective. But suppose instead that you just had t over here, right? Which maybe seems, at least to me, as the reasonable like modification to make, right? Well then, because you have t over here, minimize t plus c0 transpose x, right? You could drive t to negative infinity, right? And this thing will go up to infinity. And so this constraint will even be feasible, right? And your optimal t will just be negative infinity. And the optimal objective will be negative infinity, and and nothing else matters, right? And so you didn't really solve the problem. Okay? But yeah, that's a very good point. Yeah. Yeah, go for it.
For the constraint, you said that can be written as a sum of squares, and you take the
Square root. But yeah, but I haven't done that part yet. Yeah, go for it.
So why is there a reason we're not including a constant term in the original objective function, like a plus d at the end?
You could.
Okay, and it doesn't change.
Yeah, it doesn't change anything. Like the objective can be linear or affine, with the understanding that the constant term only affects the p star and not the optimizers, right? Because no matter what you make the objective, the constant term will still stay the same. Yeah. And in a world where we like only really care about the optimizers, then it doesn't matter. Good. Okay. So by the way, that same reasoning applies to like any convex or any optimization problem in general. If you don't care about like the optimal value, and you just care about the optimizers, then you don't need any constant terms in the objective. Yeah. Okay, good. So now, almost done. And from here, no more tricks. So I can write this as if and only if q 1/2 x q norm squared plus 1/2 minus t squared less than or equal to 1/2 plus t squared. Okay? And now we get to take square roots on both sides. Okay? So what is the square root of this thing? It's the true norm of this block matrix. Q square root x and then 1/2 minus t less than or equal to 1/2 plus t. And the reason we can do that is because 1/2 plus t is always positive because t is always positive because x transpose qx is always positive. And so 1/2 plus t is always positive, and so square root of that thing is, that's only ever going to be a positive number. Okay.
Couldn't it be 0?
Yeah, sorry, non-negative is fine. Yeah. Okay, so yes, so this is now a norm, two norm. Oh yeah, go for it.
So where did you get that matrix?
This one?
Yeah.
So if we take square roots on both sides here, then the first component of that square root is going to be, so okay. I guess it's fine if I use the third word. So if you do, okay, so this is true. So the following is true, okay? So if you have a block matrix A and B, and you take its, if you have a block vector, let's say, even in this context, A and B, right? And you take its 2 norm squared, is equal to norm squared of A plus norm squared of B. Okay? And if you just apply the same thing here, the first entry, norm squared. Second entry, it's a scalar, but you take it's squared. And so what you get is that you get that, okay, well, you can write it like this. Okay, if that makes it easier.
Wait, but like you're taking the two norm of a matrix.
It's not a matrix. X is a vector. Oh, shoot. Sorry if this is confusing. Yeah. X here is a vector.
Oh, that's a. Oh, okay. Sorry. So that's one, like negative 1/2 t.
Negative 1/2 minus t.
Oh.
Wow, my handwriting must really be bad. I don't think I've ever had that reaction. Jeez, sorry about that, guys. No, 1/2 minus t. Yeah.
So the thing with taking the two norm of is that's a vector.
That's a vector, yes.
Okay.
Oh yeah, go for it, yeah. The thing inside here is 1/2 minus t. The thing inside here is 1/2 plus t. Yeah. Yes. Yeah. So is always positive, or yeah, it's always positive even, because t is greater than 1/2 x transpose qx, right? And x transpose, because q is PSD, x transpose qx is always greater than or equals 0. So t is always greater than or equals 0. So 1/2 plus t is always greater than or equal to 1/2. That's positive, yeah. Okay, so now square roots away. And now we just have this constraint. Okay, so the thing inside this norm, if you could somehow read my apparently terrible handwriting these days, if you can, yeah. So the thing inside the norm is an affine function of both x and t. Okay, you can write out the matrix A explicitly if you want, and yeah, so it's affine function of both x and t. The thing on this side is affine function of both x and t. In particular, just t is fine, and so this is a second order cone constraint. All right. So this problem over here, let's say this problem over here with the slack variables, let's call this 4 star, okay, is equivalent to this problem, which is min x comma t of t plus c0 transpose x subject to q 1/2 x q square root x, and then 1/2 minus t. Oops. 2 norm less than or equal to 1/2 plus t. Oh, geez. Less than or equal to 1/2 plus t. So that's a SOCP. Okay, so QPs are SOCPs. You could also show that quadratically constrained QPs are also SOCPs. Good. Sorry, was there a question? Yeah, go for it.
So, I use this constraint. Do you mean to expand x by adding t to x, so it is look exactly like the original object function?
You could do that. For convenience sake, I'm not doing that. But you can imagine that it's an affine function of both x and t. This is just equivalent to saying it's like ci transpose x above there, which is affine, or ci transpose x plus di, again, affine function of the optimization variable x. Yeah. So if you want to do that, yeah, you can. And yeah, go for it, yeah.
So for the standard QP,
Yeah.
you always PSD?
Standard, no, there are non-convex QPs.
So for this problem, we
Yeah.
also assume that Q is PSD,
For this problem, you assume that Q is PSD.
but not always.
Not always, yeah. So the reason, again, is that SOCPs are convex programs. Okay? We cannot turn a non-convex QP into a convex SOCP. I mean, that's like hard. That's like, you should not expect that to be true. Yeah. Yeah. Okay, good. So a couple more things. How am I doing on time? Okay. This is a little bit awkward. Okay. So what about SOCPs and duality? Okay. Right. So we just covered this whole toolkit of duality. In the case of LPs and QPs, we used it to some benefit. At least I think that was covered in your lectures. What happens with SOCPs and duals? Okay, so you should have seen that the dual of LP is LP. You should have seen that the dual of a QP is also a QP. You guys did see that in lecture, right? No? Yes? Okay, well, that's true. So, and in this case also, the dual of an SOCP is an SOCP. Okay. And the proof is actually quite involved. And unfortunately, it's the first of 3 things I have left on my sheet, which will each take more than 5 minutes. And we have 5 minutes left in lecture. So this puts me in a kind of awkward spot. So the thing I'm going to do is not prove this. You could check the proof in the reader. And instead what I'm going to do is I'm going to motivate another example. And probably I'll post these notes online and you can read the resolution. Okay. Where's the eraser? Oh, there's a eraser over there. Okay. Okay. So the thing I'm going to motivate is a linear program with so-called chance constraints, probabilistic constraints. Okay. So you consider this linear program. Consider this generic linear program. Min x in Rn. C0 transpose x, subject to AI transpose x, less than equal to BI for all I. Okay, so this is some kind of generic linear program, and we know how to solve this problem efficiently, right? We covered that 2 lectures ago. I mean, it's a generic linear program. You can use many algorithms on it: interior point, gradient descent, simplex, whichever. But in several cases, this is not quite enough to model a problem that we want, okay? In the real world, in particular, we have, we don't, okay, so in particular, when we collect observations AI from the real world, we expect them to be noisy, right? And so this should, if you have some kind of data science or other context, which I'll go into in a little bit, this should sort of be reminiscent of certain things. So, for example, if we collect the AIs as data, and this is kind of and we say that BI are some kind of system properties, then if AIs are always data, then we can, and there's some randomness, we cannot always ensure that even for feasible x, we cannot always ensure that these constraints are met. Okay, because if AI has some randomness, then there's some probability that these constraints are not met, even for the best x possible. Okay? And so we can actually formulate this in terms of probability. We could actually formulate a separate linear program, which will get us that the constraints hold with high probability. Okay? So I'm going to write probabilistic. So just write prob min over x of C0 transpose x. So the C0 is maybe some fixed cost. When the C0 changes, this is also called stochastic programming or stochastic optimization. We can actually say that probability over AI of AI transpose x less than equal bi is greater than equal to some thresholds, probability thresholds pi that we set beforehand. So we want the probability of violating constraint I to be less than 1 minus pi. Okay, so these pi's are pretty close to 1. You could say, in particular, pi is 0.99. Pi is like 1 minus 1 over the number of atoms in the universe, something like that. And then this gives you another problem to solve. Okay, so in most cases, this problem is like equally very hard to solve. In fact, I have in my notes an example with the stock market, which shows that if you could solve this problem all the time, you'll make $1 billion. Okay, and this problem in general is very hard to solve. However, there is a representative case of problems which are not impossible. And in particular, when you work it out, the simplest possible way to solve this problem will manifest as an SOCP. Okay. In particular, if the AIs are Gaussian random vectors, so random vectors being vectors whose entries are random variables, and Gaussian random vector is just a random vector whose entries are Gaussians. This implies, and the derivation is not super long, but I cannot do it in the remaining like 30 seconds I have. This implies that this problem is an SOCP. Okay, so if you want to solve problems with robust constraints, like probabilistic constraints, you have to use SOCPs at the very least. Okay, and I think I'm out of time, but thanks for coming.